So, good afternoon, good morning, good evening, depends on where you are in the world. So, thank you very much to join us again for another exciting CASS talk. So, today we have the pleasure to have here Professor Dayane Reis from University of South Florida in USA. So, but today we are here to attend the talk by Dayane Reis. So, Dayane Reis is assistant professor in the Department of Computer Science and Engineering in the University of South Florida in Tampa. Uh, Dr. Reis received the PhD in Computer Science Engineering from the University of Notre Dame in US in 2022. She also received the Master in Electrical Engineering from the Federal University of Minas Gerais, Brazil in 2016. Dr. Reis' research exploits beyond CMOS technology for the design of hardware accelerators that can be used in a wide range of data-intensive application scenarios. She is the author of more than 25 articles in journals such as IEEE TVLSI, IEEE TCAD, IEEE Design and Tested, and Nature Electronics, as well as a renewed conference including DAC Date, ICCAD, ISLPD, and ISPDAC. Dr. Hayes was one of the two winners of the Best Paper Award of the ACM IEEE International Symposium on Electronics and Low Power Design in 2018, and a recipient of the Cadence Women in Technology Scholarship in 2019-18, and in recognition to her efforts towards the inclusion of women in STEM fields. So thank you very much, Diane, for accepting our invitation to give this talk in a very hot subject. And the floor is with you to start your presentation.
Thank you very much for the very kind introduction. I am, as he said, I am Dayane Reis, and I am assistant professor here at University of South Florida in US. And today I will talk about devices, circuits, and architectures for data-centric computing. So this is the outline for my presentation. I will start by introducing, so what is data-centric computing? What is the challenges involved with data-centric computing? And then I'll talk about emerging technologies. So what are emerging technologies and how we exploit the characteristics of emerging technologies for data-centric computing. Then I'll give some examples of how to do design for machine learning applications. So this design is mainly focusing on accelerators, which will be closing the gap between the memory and the computation. And then the last part of my talk, we talk about design for secure computing. Besides machine learning, I also work with security applications. So I'll talk a little bit about this as well. And I call this my presentation. Every time we see this green diamond, that means it's a contribution that I've done with my research, because there's some background also, mixed in the presentation. And also, to conclude, I'll talk about some future work directions, especially for computing memory, which is, a computing paradigm that I will talk a lot in this talk. So what are, the research needs in this area? So I will mention some of the directions beyond this presentation. Okay, so with this first part, data-centric computing. The data-centric computing is, we know that nowadays with the rise of big data and Internet of Things and computing in the cloud, it results in lots of data, because the models, especially you talk about machine learning models, they rely on data to be trained and learn. They also generate lots of data because the models, they have lots of parameters. And if you think about all this data, the data needs to be stored somewhere, right? So we need technology, we need devices that can be used to build memory in a very efficient way. So that's the first part, is storage. Now for the processing, we know that usually the data is stored in the memory and it's processed at processing units. And there is a gap between the storage and the processing. in traditional phone Newman machines. Um, so my research also looked into how to address this gap in process data in a more efficient way, reducing the memory transfer. Now, last part is that all this data, some of the information that applications generate and work with is protected, is sensitive. So security and privacy are concerns when we talk about big data. And so I will talk a little bit about how to protect the data and how to do it efficiently. Use accelerators to do, data protection. So when I talk data computing, this is actually data-centric computing. This is actually what I mean. These three parts: storage, processing, and protection. Now, given these challenges, which means like we have this large volume of data that we need to store, we need to process and protect. What is the solution that we can employ to make this more efficient and specialized? The solution that I work on is called cross-layer design, which means given, for example, given application. So it can be here you have some models, for example, feature of learning, also cryptography. You have the application. So what are operations that this application needs in order to run? So for example, if you talk about machine learning, neural networks, we need lots of matrix multiplication. You need also addition. You need, for some cryptography operations, you need modular reduction, search, etc. So you look at these operations, and then you look at the architectures. So how this architecture should be specialized to support the operations, so that you can, gain some speed up, energy efficiency, so on and so forth. Now, the architectures, they are higher level abstraction. Then you need to talk about the circuits that are employed to build these architectures. So the circuits, for example, could be memory crosswires that can be used to do multiply matrices and vectors in a very efficient way, content addressable memories, etc. So these circuits, when you put them together, you can actually build efficient architectures. Now the circuits, when you're building the circuits, you need devices, the transistors, because they are the main building blocks. So if you make them efficient, of course, all the levels on this cross-layer design stack will benefit from it. And as you know, the CMOS, at the scaling, the devices are shrinking. It has some problems with respect to the leakage power, for example. So now people are researching new devices that can enable all these stages that I talk about, the circuit, architecture, and so on and so forth, to be more efficient. Okay, so this cross-layer design is what I do, and there are actually two ways you can look at this. You can look at as bottom up, so you can really start researching at the devices, and then once you have a device, you look at the unique characteristics of that device, and then you design a circuit to leverage them. Okay, and then you go up. So this is the bottom up view. From the top down perspective, it's more like you have the application, you have the need of that application, then you're gonna try to find the architecture that suits that need. And also there is a concept that is called hardware software co-design, which means that once you have this architecture, maybe you have to write your code, your software, to leverage the characteristics of the architecture in a better way. Now, I will in this talk I will start talking about the devices first, the emerging devices, and then I will build from the bottom up with this solution. Okay, so emerging technologies, emerging devices, as I mentioned, scaling. The scaling, as we scale down the transistor size, you have problems associated, especially with the leakage power, for example. There's a physical limit, right, of scaling. So the researchers and the companies, they're like working on solutions like 3D and all these to try to you know to uh, to overcome this problem. Now, there's also emerging technologies which are transistors or devices that they have the characteristics that are very unique and that they can be used in a different scenarios, like to build memories, uh, and also some of them are bipolar. Then you can use them in hardware security. So there are several scenarios that we can use emerging technologies. Some of the examples of these are, for example, SOT and RAM, which are magnetic, also resistive RAM. They're devices that they have variable resistance that they are programmed. They can program with current. Like when the current flows, and you have a material that you change the structure, the organization, or something inside the material, and achieve different resistance. Now, we have also ferroelectric FETs, and here is another type of ferroelectric FET, which is the back end of line FET. But the principle behind this is the same. So they are transistors that they are programmable through the ferroelectric polarization. So I have a separate slide about ferrofets that I explain and how they work. And also flash memories, which are programmable, and they have like floating gate transistor structure. And they are they could be employed to build less level caches, for example. So here we have all these emerging technologies. It's very important that we map the type of, the circuits that we're going to develop to the appropriate device, right? Okay, so now one device that I work with this device quite a lot, and not only me, but other people in the research community. They're called ferroelectric field effect transistors. The symbol is the symbol with this blue part in the middle of the gate, which indicates that you have a ferroelectric layer of a ferroelectric material inside the gate stack, and that ferroelectric material gives you hysteretic behavior, so it gives you memory. So the device, the ferrofet, you can program it, and it doesn't need power supply for the information to remain stored inside the transistor. So it's like a transistor with memory, right? And you have this concept that is called memory window, which is, in this case, memory window in this figure is, example, 0.9, which means that an applied a gate voltage within this interval here, we're going to read the device. So whatever you store, so to store you need either a higher negative voltage or a positive voltage on the high end here, and then intermediate voltage, you're going to read the state of the device. So as I was saying, this device works with both a switch and a memory. There are some fabrication prototypes available from MANLab, Global Foundries, and others, and research labs around the world. And it's a very promising material, and the transistor, because it has this three-terminal structure, and it's the fabrication process is compatible with CMOS. So people have been working on this a lot. And CIM, which is computing in memory, there are lots of ferrofet-based computing in memory circuits and architectures that are proposed in the literature. Some of them CASS2, Nature Electronics. One of the most famous of this is the ternary content addressable memory that can be used to do like search operations and nearest neighbor operations. And also there is this GPCIM, which is general purpose computing memory, which tries to build like a general purpose processor inside the memory. So this is what this is actually my work. It was published in ISLPD 2018. So besides using this device for memory, it is also used for computing in memory. So it's actually trying to address the two challenges that I talked in the beginning of the presentation, which is with the storage and processing. So this device can be useful for both, right? Now, for memory, when we talk about memory, it is very interesting that it can build a memory array, which is like each cell is just one device. So you have one surface bit cell for each memory cell. So it's very complex compared to, for example, SRAM. So each SRAM cell, there are of course several designs, but usually it requires you to put six transistors to build one SRAM cell. In comparison with FAT memory, you only need one. But there are some drawbacks, which, for example, for FAT you need a higher write voltage than for CMOS SRAM. And as this memory structure, it doesn't have selectors, so you need some bias inhibition write schemes to avoid disturbance, which means that imagine that you're trying to write 1 to M21. So M21 is this transistors. To write 1, you need to apply 4 volts to the gate of this transistor and 0 volts to the source and drain of this transistor. Then you write 1 at that transistor. However, if you do this, as you have like shared word line here, that means you're also applying 4 volts to the neighbor transistor. So you need a inhibition bias write scheme, which means that you apply intermediate voltage here at the source and at the drain of M22. In this case, this intermediate voltage is 2 volts. So that instead of having VGS of 4 volts, you only have a VGS of 2 volts, which means that this smaller VGS is not able to switch the polarization and write at these transistors. So you only write at these transistors. So as you don't have access transistors for the memory cells, you have to play with these things. For example, inhibition bias write scheme. Yeah, and there's several types of inhibition bias write schemes. So there are, for example, VW over 2, VW over 3, which means that they are just different levels of the voltage that you're going to apply to the source and drain. Okay. Now, these schemes have been proposed in literature, but they don't consider the impact of the body voltage at the writing of the transistor. And my work addresses that. So what I did in my work is to propose a way of avoiding these disturbs. And that way it takes consideration the body potential. So it's called column-wise body. So usually to have a regular array like this one, the body connection is shared for all the arrays. Now what I propose is to separate per column. And separating per column, what I proved with my research is that we can reduce the impact of the disturbs in unselected cells. Okay, so here in this graph, what we can see is the comparison of different write schemes, and some of them they have the shared body for the whole array, and some of them that have only the column-wise body. And you can see, that here is the VFE, so it's the voltage across the Ferroelectric, and you can see that the ones that have shared, so this one in green here that has shared body for the whole array, so they disturb more. So you can see the more the line is separated from this baseline here, that means that it's more disturbance. So yeah, so this is what this graph is trying to show, right? Now for schemes that have the same column-wise body, column-wise, then they're closer, like this red one here, closer, the disturb is closer to the baseline. Yeah. Now, this work, this is a work of mine that is trying to prove the resilience of this one terabyte memory against write disturb. Now, I took this to another level, which is using this one terabyte base memory to do in-memory computing, right? So now we are going to enter in the design for machine learning application space, which uses in-memory computing. Okay, so what is in-memory computing or computing memory? So I'm going to use these terms interchangeably. Okay, so computing memory is a type of computing paradigm that tries to reduce the data movement between processor and a memory. Okay, so what it does is to make significant logic and memory on the same chip. When I say on the same chip, there are different, flavors of computing memory. So some people are really leveraging the memory cell to do computation inside the memory cell. Some people are doing it at the peripheral level, which is I am doing. So what I do is to modify. So have a memory array. So you have sense amplifier. You're going to augment or modify your sense amplifier design so that instead of only doing reads, it can do reads and compute between, if you have two memory words selected here at the same time, then it can compute between these two memory words and we have to transfer them out. So this is also computing memory. And there's also near memory computing, which is you have your memory and then you're gonna put some functional units near the memory on the same chip, but near the memory, and you still have to transfer your data from the memory array to this functional unit. Okay, so there are several types of ways of trying to, to bridge this gap between processing and memory. Now, the one terabyte memory is a design that we can do. So if you use that memory that I showed, you can design peripherals that allow you to, to compute between two of the rows of that memory. And when I say compute, what I mean is you can do this type of operations. So you can do logic like AND, NAND, XOR, XOR, or NOR. You can do arithmetic, addition, subtraction, and multiplication and division is a little bit more complicated. But what we do within the memory computing in my work is that we only can do division and multiplication by powers of 2 with bit shifting. So you can implement, you can design a shifter at the next level of your sense amplifier so that you do multiplication and division by powers of 2. Now, computing memory with surface, this is the overview. So what we have is the customized sense amplifier because the computation is done at this level. And we have a Ferroelectric cell, which I showed as the Ferroelectric memory. And then we have also to modify the structure of the array by putting an extra decoder, which means that this decoder is used now to select two of these rows at the same time. So you select two of the rows and then you sense both. How you sense both? Oh, there is an animation here, so this was lost, but I'm gonna explain. This is the sense amplifier that is used for in-memory computing. So here, this is the bit line. So your current, when you select two rows, is gonna flow through this bit line. It has some circuit. So this middle part is pretty much the regular sense amplifier that will be used for read. You have a reference cell here. So you compare the current that flows through the bit line to a reference and generate a response. Now we augment it and put some logic gates around it so that now And when comparing with the reference, now you can generate things like AND or XOR. And now we use this bitwise logic, and the result of the bitwise logic we can forward to a separate secret that we compute for you sum and carry. So with this structure, we can do Boolean logic and we can do basic arithmetic, addition. Now, subtraction we can also do, but we need multiple steps. Right? So we need first to negate the first operand, then you read it, and then you write it back, and then you can add. Okay, so you use addition to do subtraction this way. Now, so I propose this in-memory computing framework with Surface, and then we evaluate it using SPICE simulations, so which means the array hasn't been fabricated yet. So the way we evaluate it is through SPICE simulation. And then what we simulate in SPICE is the Surface itself. So we have a module that is based on the fabricated device. So that you have a fabricated surface. You're going to collect measurements from that fabricated surface and build a Verilog A model, and that's what we use in HSPICE simulation. And I also implemented this customized sense amplifier from last page. Now, you can only simulate in HSPICE arrays with limited number, of rows and columns. If it gets too large, then it's hard to simulate with HSPICE. So then we use Destiny, which is a memory simulator. So a memory simulator, it can, besides doing only the array part, can do all the components of the memory, and you can, have a bank structure. So we integrated the results of HSPICE into Destiny, the memory simulators, and with that we could evaluate a 1 megabyte memory array that is made of Ferroelectric and also S1. S1 is for the sense amplifier. Oh, sorry, S1 it was a baseline. So we did it with Ferroelectric and also did computing memory with S1 to compare, to kind of separate out the benefit from the architecture from benefit of the technology, the Ferroelectric itself. And what I was going to say actually is that all the peripherals and the sense amplifier circuits, they are of course with CMOS. Okay, so yeah, and once you get this, what we measure is the energy and latency for each operation. So assume that I'm doing addition between two memory rows. I select the rows and then do the addition, and then I measure the energy and latency for this operation. And I can do it for all types of operations that my memory computer is able to perform. So I have the cost in terms of energy and latency for the operation. Now, I have the other part of the evaluation, which is the application level. So we're getting memory access traces from different benchmark programs. And these are from the literature. And based on the memory access traces, we know how many adds this application demands, for example, how many reads, how many writes. And based on this quantity and the cost of each operation in memory computing, you can actually estimate the cost of doing this application within memory computing, and then compare it with something like a CPU or GPU, for example. Yeah, so here on this slide, I'm just showing for the system level evaluation, the application level evaluation, the benchmarks that we're using, the programs. So for all these programs, we categorize the memory access into three different types: writes, reads that are CIM friendly, which means that these reads triggered in the memory, we can replace two of these reads, so because we're assuming that we're fetching two operands and sending them to the processor. So you can replace two of these reads by one in-memory computing access. So these are CIM friendly reads. And not CIM CIM-friendly reads are those that cannot be replaced because the operation is not supported within memory computing. So here we have the percentage of not CIM-friendly access and CIM-friendly access. So we have these two. And for CIM-friendly, just a reminder, what we do is two of these will be replaced by one in-memory computing access. Okay, so we have these percentages, and with these percentages, we can estimate the application level benefit of in-memory computing. And note that I highlighted here in purple some applications. They have actually high percentage of writes. So we'll see what happens with this. Writes, we cannot reduce the writes with in-memory computing. Right? We can only reduce reads, not writes. So, and we have the SRAM baseline. So everything here is normalized to the SRAM. So they have energy comparison and latency comparison. And you start analyzing the ones that are highlighted in purple. We observe less improvement with the write-intensive applications because they cannot really take advantage of the reduction in write. And even in some cases, it's worse than SRAM. And we also, of course, we included another technology here, which is SCT. SCT also, in our paper, we analyze SCT and Ferroelectric. And for SCT, and even some cases for Ferroelectric, you can see that's worse than SRAM. And that's because the writes with Ferroelectric and SCT, they are quite slow. And they, you can see here for latency and energy. And especially for SCT, the write is current-based. So the write also consumes lots of energy. But for the applications that they don't have as many writes, they're more reads, then you can reduce the energy and you can reduce the latency because you're avoiding some of the memory access. And this is the percentage. So it's 60% faster. The Ferroelectric CIM is 60% faster than SRAM, and 40% faster than STT. And here is for energy saving. The numbers for energy saving, 30% and 40%. Okay, so this was the first work that I actually did in memory computing. Now we used in-memory computing for some more specialized applications, like few-shot learning, for example. So few-shot learning is a type of learning that allows the network to learn from just a few examples. So imagine, for example, that you train your network to recognize, let's say, classes, like 5 classes. Then you want to add a 6th class into this network. It might not be possible if you don't retrain it from scratch. But with few-shot learning, we have a process that is called mini-training. That is uses, for example, if it's a computer vision application, so you're going to have a support set with some support images. And with a very small set of images, you can make your network learn this 6th class. Okay, so this is used to, to kind of make your model to adapt and to incorporate new information in an easier way. And this is, of course, you requires a model to do this few-shot learning, to do all this, the learning process and the classification. And the model that we look into is memory augmented neural networks. Is an attention-based model. So you have what we call attentional layer, which is highlighted here. And the way it works is that you have you support images for each class. You're gonna get the feature vector from neural network, and you're gonna store the features in the DRAM. So you keep storing features in the DRAM, and you're going to compute the distance with the GPU. So you compute the distance when a query comes in. It goes through the neural network. It gets the feature vector of that query, and it will compare against all the images inside the memory. Now, this comparison can get quite expensive because to compare, you need to compute distance in your compute unit, and the data is stored in the memory unit. So you need to transfer all your entries from the memory unit to the compute unit and compute the distance. So it can get quite expensive. So that's what I'm showing here, the data transfer. There is a data transfer bottleneck. And also, after you generate your classification, you should update the memory unit so that your network now it learn a new class. So you update your memory unit. So the process, it has lots of transfers between the memory unit, the compute unit, so on and so forth. And these data transfers are the bottleneck. Okay. So here, I'm showing a graph showing for each stage, for the training and inference, what is the percentage of the attentional layer operations compared to other operations. So for inference, almost 80% of the operations are related to the attentional layer. Okay, so we accelerate, the conclusion here is that when we accelerate the attentional layer, we can accelerate the future of learning. Okay, so what we do is we have this design, it's called AIM, attention in memory. Again, it's a Ferroelectric-based design. And the difference between this one and the other one is that this one is configurable, which means that you can achieve multiple functions inside with the same array. For example, we can do the type of in-memory computing that I mentioned, which is more general purpose with a Boolean logic and arithmetic. We can also do ternary content addressable memories. So as you can see here from MEMS, we're going to do a comparison against all these memory entries. So if you can actually do it in parallel, that would be very beneficial. So we're using TCAMs to allow us to do that, to make this comparison more parallel. Because the CAM, the content addressable memory, it searches all the entries in the memory at the same time. So we incorporated the TCAM element, and then on top of it, we're also using general purpose computing memory. Now, because we're combining these two functions with the same piece of hardware, now it turns out that the structure of the array needs to be different. We cannot just get away with one transistor per cell. So we need to insert excess transistors. And so that cell gets a little bit bigger when we do that. Now, how do we map the memory augmented neural network to this hardware that I just showed? Now, when we're going to do the comparison, we do a similarity search with the TCAM mode, which means that we compare the query with all the entries using the TCAM mode. So you can do a very parallel search across all the entries. And then, but it turns out with doing this, the accuracy drops quite a bit. So what we do is with these entries that we kind of filter, we do a Manhattan distance using the general purpose computing memory. So Manhattan distance requires subtraction between the query and the entry, and then accumulation. And this type of distance is computing memory friendly. So you can do with general purpose computing memory. Now, with the same piece of hardware, we can do both, and you can get quite good accuracy. Now, evaluation setup is very similar to what I presented before. For computing memory, we execute the network and the GPU, and you get the operation breakdown. The data set we use is OmniGloss. A neural network is also from reference one here. And then we do circuit evaluation with a simulation-based H5, measuring time and energy for each operation at the circuit level. And then we put these two things together, as I explained. Now, also, we investigate different setups with respect to the hardware type and the distance metric. So I explained this combined function, TCAM and GPCIM. And we investigate, besides investigating GPCIM with configurable configurable functionality, we also do it with separate hardware, which means that we have a piece of hardware to do the search, the similarity search, and then we have another one to do the general purpose computing memory, the Manhattan disk. So this is setup C with separate hardware. The setup D and E are the configurable, but they are two different words. Okay, the N, which is my work, and Ferromet, which is another word. And this is the distance metrics that we implement. And we also compare with the TCAM and LS using the LSH, an LSH approach, which is another reference. And of course, the baseline setup A is doing this at the software level only. So without any accelerator. We do with the GP, GPU, and the event. Now, the improvements that we get, so the improvements are all normalized to the GP, GPU. So setup A, we can see that for our setups, B, C, D, and E, we can get, so this is the phases, the distance metric, memory update, and the whole of the attentional layer. So you can get around 36x, 32 sometimes x delay improvement with a minimum of 9.6x energy improvement for our setup. And end-to-end, so including the network and all these, is around 4.4x for all of them. But then if you compare the accuracies, the one with the configurable, the end and work, it has better accuracy than others. Of course, not than GP, GPU, and the event. That's the baseline design, but you have a little bit of accuracy drop, but as a trade-off, you have delay improvement around 33x and energy improvement around 26x for attentional layer and 4x4x end-to-end. Okay. Now, the last part, I talk about security. So I will just talk a little bit about my work on security, which is we have all this data. So it's very important that we care about how to store it and very efficiently, how to compute it, and also for some scenarios, a lot of scenarios actually, it's very important that we have solutions to secure the data. So one thing is enable private data processing, which means that imagine that you have a cloud server and you outsource your data to that cloud server, and you can encrypt with things like AES, for example. You can use normal protocols to encrypt your data and store it in the cloud. But if you're running machine learning on the cloud, the machine learning it cannot run on encrypted data with normal encryption. That means that you must decrypt your data before doing training or inference on the cloud. And that's a concern if you think about privacy. If you want to preserve the privacy of your data, you don't want a third party to decrypt your data, to have access to your data. So privacy preserving machine learning is, it's very important. And one of the ways of achieving this is with homomorphic encryption, which is a special type of encryption that allows computation to be performed on encrypted data. So it has lots of mathematics behind it, but there are also several schemes that can be used for HE. One of these schemes is SV. So SV, homomorphic encryption, is a polynomial scheme, which means that it computes, it operates with polynomial. So all the operations that we do are polynomial operations. Polynomial addition, multiplication, so on and so forth. Now, the problem with HE is that the ciphertext space can get pretty large. So, for example, to encrypt a 32-bit word, for example, that requires you even like a few megabytes of data to encrypt just one small word. So imagine that the ciphertext is pretty large, and it triggers a lot of data transfer inside your your computer. And that's one of actually the reasons why HV is not even practical. It's not, it's not widely used because it's very computationally expensive. So what we did is to design a circuit that supports HE inside the memory. So this is the circuit, just very high level details about it. And different from the other ones, we needed to now include bit shifter because we do lots of bit shifting to support new operations, and we need a sequence and circuit, which is a controller inside the memory. Yeah. Now, the benefits we got from it is we can get performance with respect to previous accelerator, like using FPGA, for example. It was 2.2x time, 88.1x energy with same parameters. And also here we set the different cache sizes also, because the cache size has influence on the performance of in-memory computing. And we besides our only running operations, which like addition, subtraction, multiplication, we also run tests like inference with NLP, with very simple network on MNIST data set, just as a proof of concept. So, and we got time improvement, energy improvement results as well. Now, AES, we also did accelerators for AES, mapping the different phases of the AES algorithm to computing memory units. And here, showing some details of the architecture, but it's basically we employ SRAM for this one. We don't employ Ferroelectric. We could employ different technologies, but our goal with this is that we wanted to prototype it, and prototype it with Ferroelectric is harder than prototype it with CMOS, right? So we actually haven't prototyped it yet, but our goal was to prototype it. So the first baseline design was using CMOS, SRAM, and what we call RAY-CAN, which cell that can do RAN and CAN. Now, this design that it has the advantage that it can work in RAM mode and CAN mode. This both modes can do, with the RAM mode, you can do encryption, and CAN mode, we can do decryption. So you do encryption and decryption with the same design. The benefits here, again, I had animation, so this is all messed up, but we tested different technologies and compare against different accelerators. So again, I have different setups, A, B, C, D, E, and E with Ferroelectric. What we observe is that the benefit of our accelerator is mainly throughput per area, so it can achieve high throughput with lower area than other designs. So when we do the ratio throughput per area, we see advantages. And also ADPP, which is area delay power product. We can also have advantages. Okay, so this is what I know it was a very high level, and I cover a lot of different works here. But this presentation is just a piece. Beyond this presentation, what I see is very important to study within memory computing. First topic is really when we say computing in memory computing, it's not great for all types of applications. So we have FPGA, we have other ASICs. It's very important that we map the applications to the different acceleration platforms. So this is one line of study that I think is very important. The second one is system level integration of in-memory computing. So how to program, so how to really do in-memory computing, in-memory friendly instructions. So how do you do this hardware software interface for the in-memory computing? And also for the security side, and also another research direction is to look into protection against sidechain attacks inside the memory. So this has been a prevalent area of research, which I think is very important. So I think that concludes my talk. Thank you very much for your time.
Thank you, Dayane. So now we are open for questions. If you have any question, please do it as soon as possible in the chat channel of YouTube. So we have here some questions by Dr. Giancarlo Absch from Federal University of Rio Grande do Sul. So the first one is, what is the main applicability of this type of technology?
Mm-hmm. Yeah, and I saw that he also asked, I think maybe his two questions are related for the IoT devices also. So that's a very good example, the IoT devices and the edge devices. So I've been working on a project right now that we are looking to integrate this type of technology into wearable and implantable devices for low power, for example, because the Ferroelectric, especially in other emerging technologies, they have very low power because they don't need the power supply to store data. So when we do this in-memory computing inside the arrays, and they are also very dense, we can build very low power sensors and compute and do things like machine learning inside the sensor to defend from attacks. So if you imagine an implantable device, for example, I'm giving this example because this is a project I'm working on. It has to be extremely low power because once it's implanted, you cannot take it out to recharge the battery, for example. So this has the advantage of the low power, which the emergent device can give you. And also you can do a fast inference for the networks that trying to detect attacks and faults. And it has to, because the sensor has to be reliable, the implantable sensor. So that will be a use case for this technology. But there are many use cases.
Thank you, Dayane. Mm-hmm. Another question by Giancarlo again. Considering that most of IoT devices are resource constrained, is it possible to apply this type of technology in the IoT edge computing?
Yeah, I think that's what I talk about. So I think these two questions are related. Applicability could be edge device. Can also be used, to do things like compute caches, which is something I worked on, so it's totally different. But a very, motivating one for me is edge device.
Okay, thank you. So the third and final question by Giancarlo is, what about the sensitivity of this technology to radiation effects, single event transient, for instance?
Okay, so I personally don't work in this area, so there are people who work in this area, investigate this. So I cannot say it's more resilient than CMOS, for instance, or MOSFET. But there are people that are investigating this. So it's not, I cannot say this is the advantage of, Ferroelectric compared to other technologies. It should be average.
Okay. So I see no more questions in the chat. If someone has a question, please do it now. I have one. You talk about hardware accelerators. What do you think about the possibility to have an architecture composed only by hardware accelerators and a small CPU to control them?
Yeah, so I think it would depend on what you're trying to do. So I think the CPU controlling them is a very key aspect, right? And I actually didn't have time to show the AES accelerator in details, but it has it has a processor, it has a RISC-V that is controlling the in-memory computing accelerator, but it doesn't have to be only in-memory computing, it can be on other types of accelerators. But I think when you integrate the CPU with it, a good advantage is that you can do like customize, you can make it more customized. You can do things like what I mentioned towards the end. You can do instructions that are created specifically for in-memory computing or for the accelerator, and other, more specialized tasks can stay with the CPU. It doesn't have to be. So you do this technology using it as more like a co-processor. So I think it's very promising, but we have to look specifically at the use case that we're targeting.
Okay, thank you very much, Dayane. I'm seeing no more questions here in the chat. So thank you again for this very nice, interesting talk in a hot subject. So bye-bye to all you. Have a nice weekend.